You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Jim Fanson and Dr. Rebecca Bernstein. Dr. Jim Fanson earned his doctorate at the California Institute of Technology in Pasadena, where he joined NASA's Jet Propulsion Laboratory. He was a member of the team that fixed the Hubble Space Telescope's blurred vision in 1993. He later served as lead engineer for the design of the Spitzer Space Telescope and project manager for the Galaxy Evolution Explorer. He now serves as project manager for the Giant Magellan Telescope. Dr. Rebecca Bernstein has had a long history of spectrographic and imaging development. She is a project scientist on the Giant Magellan Telescope project, an international consortium where she will provide technical and scientific leadership for the design and construction of the telescope. She received her A.B. in physics from Princeton University and her Ph.D. in astrophysics from Caltech. She was a Hubble and Research Fellow at Carnegie.
James Fanson and Rebecca Bernstein, welcome to the program.
Thank you very much.
Thank you.
Now, the Giant Magellan Telescope is probably one of the most exciting things in astronomy that's coming down the pike, this huge, enormous telescope. So I want to give everybody an overview of exactly what this telescope is, how it's being built, and where it's being built. So let's start with the location. Chile, in the Atacama Desert in the mountains. Why?
Well, the placement of a telescope on the ground looks for several things. You're looking for a location where you have a lot of good, clear night skies for observing. You want a place that's in a dry area so that the water vapor in the atmosphere above you that you have to look through doesn't absorb too much light. And you'd like a place that's dark. And so there are a few places on the Earth that are really superior for those conditions. And the Atacama Desert in the Chilean Andes is one of those locations. And in fact, there is an existing observatory there. The Carnegie Institution owns a large parcel of land, and they have placed their telescopes there since the 1960s or 70s. And so they are one of our founder institutions, and they've offered that location for the Giant Magellan Telescope.
I can give you a little bit more general answer about what makes a good site. Jim described it perfectly, and the geographical conditions that generally lead to the kind of site Jim was describing are a mountain range on the western edge of a continent. Because as the atmosphere moves from west to east around the planet, the atmosphere has a nice long time to become smooth and more laminar, choppy, as it's moving over an ocean. So that nice smooth air gets to the edge of a continent and it's still smooth as it's, for a little while above the continent. But then as you go further into the continent, it gets more choppy. So a high mountain range will get you above a lot of the atmosphere. Having that atmosphere be nice and smooth and laminar because it's just come off an ocean is another good thing. So mountains at the western edge of a continent, and the high Atacama Desert over the Andes is exactly that. So that's why the Andes, as Jim was describing, are a great location.
Now, is there any sky glow, light pollution present, or is this place just so remote that it's not even a concern?
Well, there is a general concern about light pollution almost anywhere that you go. We're located in an area that's still very dark, but there's an active light pollution control effort between all of the observatories in Chile and the Chilean government. And there are laws and regulations and so on to control lighting to minimize the impact. But as metropolitan areas grow in size and as mining operations expand, we are aware of a certain amount of light pollution. So it's something that we monitor, and we work with the authorities through regulation and enforcement, and just generally education and persuasion, try to minimize the impact of light pollution. But we're in a very dark site, in Chile. It's very remote. It's like a 2-hour drive from the nearest city of any size. It's not really an issue for us at the moment, but we keep track of it to protect the future.
Now, this area of Chile, nothing's ever perfect. This area of Chile is a seismic zone. So what steps have you taken in regards to earthquakes and the telescope?
Well, that's an excellent question. So Chile is a very seismically active area. In fact, the largest recorded earthquake in history occurred off the coast of Chile in 1960. So we have incorporated into the design of the telescope measures to protect the telescope from ground motion. And this is really the first time this has been built into the design of a telescope, optical telescope on the ground. So our strategy is to place the telescope, which sits on a large concrete ring wall, which we call the pier of the telescope. The telescopes typically are mounted on piers, large masses of concrete. But instead of bolting the concrete to the ground, we're going to place that ring wall on 24 what are called seismic bearings or seismic isolation bearings. And what this will do is allow the pier wall to remain fixed, if you will, or allow the ground to move underneath it. And what that does is, at least in the lateral direction, it decouples the telescope from the ground motion to a large degree. There's still a vertical component. There still is a transmission of force through the telescope pier into the telescope itself. But that isolation system, which is commonly used for bridges and buildings and so on in civil engineering, never been applied to a telescope before. So it's a new application, but that is the primary measure we're taking to protect the telescope. And then in addition, we are building in dampers into the support system of the large glass mirror segments so that their range of motion, which is amplified by the structure of the telescope during an earthquake, so that range of motion remains limited.
How much weight are we talking about, the whole telescope assembly sitting on top of this cushioning system?
So let's see. So the mass of the telescope is about 2,000 tons.
So that's a huge amount of weight sitting on the system. Now, Rebecca, I have a question for you going back to light pollution. As urban areas, I know the lifetime of this telescope is projected to be on the order of 50 years. As the urban areas in Chile grow, presumably the light pollution in the area will also grow. Is there any way to filter this out in observation?
There really isn't. And in the past, when cities have grown up near observatories, they've tended to make those observatories much less useful. So for example, there's Mount Wilson just outside Los Angeles, in fact, just outside of my window here in the Angeles National Forest. And as Los Angeles has gotten brighter and brighter over the last century, Mount Wilson's effectiveness for science has been limited to the infrared, where the city is not, wavelength range where the city is not bright. Once you get a lot of light pollution in the area of the telescope, it really does limit its use.
Now, what about, I know there's quite a bit of discussion lately about satellites and constellations and things like that interfering. Is that something that can be mitigated?
Again, that's a very tricky problem. The best way to mitigate it is by reducing the brightness of the satellites themselves, and by limiting the range, the area of space that they might occupy. So there are lots of discussions going on already with the company talking about putting those satellites up and trying to mitigate the impact they'll have that way.
I suppose the last of the natural concerns with the telescope is wind. I'm sure it gets pretty windy up there in the mountains. What do you have there to protect the telescope?
So we have what we call an enclosure, which is a large rotating building, essentially, with biparting doors that open and shutters that can open to allow ventilation. So it's a structure that works in concert with the telescope. It moves as the telescope moves. And during the daytime and during inclement weather, it protects the telescope from the elements. It's also used in the assembly and maintenance of the telescope during the day shift. So this is a building that's about 60 meters in diameter and about 65 meters tall. So it's quite a large and sophisticated building. And it's, of course, the thing you're going to see when you drive up to the observatory. You're going to see from a distance this large enclosure structure.
Now, grinding the mirrors, casting and grinding the mirrors is an interesting process because the mirror is melted and spun and then very, very carefully controlled in cooling. From start to finish, how long does it take to make one of the segment mirrors for this telescope?
So if you start from when you actually start building the hearth that the telescope is cast in, all the way through the completion, the polishing to the final surface figure specification, it takes about 4.5 years or so to fabricate one of these mirrors. It takes about 22 months to build the mold and place the glass in the mold and heat it up and flow it into the mold and let it slowly cool down and anneal and clean, all of the mold material out so that you're left with the glass casting. That takes about 22 months. And then it takes about 9 months to prepare the rear surface, which is where the mirror is supported on the control system, all the actuators and so on that attach to the back of the mirror. And then it takes a little over 2 years to grind and polish the front surface. It takes about 6 months to get to about 1 micron RMS surface figure, and then another 14 months or so to polish to final specification, around 20 about 20 nanometers RMS. So it takes a long time, and there's only, for example, one polishing machine at the Keras lab where these mirrors are made, interestingly, underneath the football stadium out at the University of Arizona. So they're what we call long lead items, and we've been manufacturing them now for a number of years, just because it takes so long to manufacture the full 7 mirrors we need for the telescope.
Now, when is first light, and when will it be fully operational?
Well, our latest schedule shows 2029 as a first light date, and that would have 4 primary mirror segments out of the 7. And then it would take another year to 2 years to complete the telescope and achieve all of the various operating modes.
Once the telescope is operational, this telescope has adaptive optics. So even though we have a very good location for seeing, it can still sort of work with the atmosphere itself. Tell us about that system. How does the telescope compensate for Earth's atmosphere?
So we have the optics on this telescope that actually do the adaptive optics correction are our secondary mirrors. So the secondary mirrors are 7 mirrors that are roughly 1 meter in diameter each, and they are matched 1-to-1 with the primary mirror segment. So the light comes from one primary, secondary, and then down to the focal plane. And these secondary mirrors are fully adaptive, meaning they can alter their surface shape to correct the turbulence in the atmosphere on a kilohertz timescale, so very rapidly. And by measuring the wavefront that we're getting through the atmosphere and by rapidly correcting the mirror to essentially form the inverse wavefront of that measurement, we can take out the turbulence, the damage to the wavefront that's being done in the atmosphere by the atmosphere as the light travels from the top of the atmosphere down to the telescope.
How is the atmosphere measured to adapt to it?
So you basically look at one star and you take the image that forms from that star and you manipulate it so that what you're looking at is the pupil image, the actual wavefront image. And then by measuring that wavefront and feeding that information mirror more rapidly than the shape of the wavefront changes, and actually correct that turbulence in real time.
It's absolutely amazing. Now, resolution of this telescope. This is an enormous telescope with much, much greater technology than, say, Hubble. How much more resolution will this telescope provide versus Hubble, or any space telescope for that matter?
We get almost a factor of 10 better images than Hubble, just in round terms. So the resolution that a telescope can get is just limited by the diameter of the telescope. So the aperture quantum mechanics, the interaction of light with the telescope aperture, the primary mirror itself, is what limits the image size. And so by having a larger telescope diameter, you get inversely better image quality. So by having that very large diameter, we do much better than Hubble.
Let's get to the science. This telescope offers a probe into the universe that's, much greater than the instrumentation than we have now. So in trying to solve mysteries about things like dark matter and dark energy, where's this telescope going to take us? What can we look at with this higher resolution that might solve some of those mysteries?
Well, GMT is being designed, basically the important things about a telescope are its sensitivity and its resolution. And with greater sensitivity and resolution, you can basically look at anything that is fainter and smaller. And that means anything nearby or anything that is intrinsically faint because it's nearby, or whether it just appears to be faint and small because it's on the other side of the universe. And curiously, the way that we study all areas in astronomy can depend on this resolution and sensitivity, whether it's planets and stars and galaxy and our own galaxy nearby, or whether questions about the formation of the universe itself, studying things at the very edge of the visible universe, or trying to understand the universe from sort of the archaeological record of things that have formed throughout the history of the universe. So when you ask what we'll be able to see and what it will bring us, the answer is it's complicated. Being able to see things at all distances help us to study all different aspects of astronomy. So I can tell you a couple of things that are very interesting, but these are the things I can tell you about in detail are things that have come up as questions for us because of what we know today. There are going to be an endless number of things that we don't even know to ask today. But some of the things that have come up recently because of what we've been doing with the telescopes that we have, so these questions that we know to ask now, these include things like, how do planets form? Do other planets host life? Even 25 years ago, we didn't know that there were other planets. We suspected that there were, of course, because if our planet formed, other planets should be able to form. But we weren't able to point to any of those planets. So in the last 25 years, we've been able to find definitively thousands of planets just in the neighborhood of our sun in our galaxy. And hundreds of those planets we now know are potentially capable of hosting life. We don't know whether they do yet, but we're able to determine that they have the right pre-existing conditions to potentially host life. So one of the things we might potentially do with GMT is study hundreds of those nearby planets to look for the biosignatures of life, the combinations of molecules that can only be found in the atmosphere of those planets if life exists on those planets. So that's one example of something that we'll certainly do. Other examples can be found in all areas of astronomy, from understanding dark matter to understanding the physical phenomena that explain dark energy or the acceleration of our universe, to understanding black holes and how black holes co-evolve with galaxies, which we already know that they somehow do, but we don't understand exactly how.
Spectroscopy in regards to exoplanet atmospheres seems to be well within the reach of this telescope for close by systems. And of course, as you mentioned, biosignatures. So if you see something that has weird oxygen levels and a little bit of methane and things that look a lot like Earth, then you can begin to ask the questions, maybe there's a biosphere there. And this telescope should take us there. What other biosignatures are within reach of this telescope? I mean, what are the principal things you would look for in an exoplanet atmosphere?
You answered the question. I think you got it. What we're looking for is molecules in the right combinations that can only be really sustained in an atmosphere if that atmosphere is being impacted by life on the planet. So water, methane, molecular oxygen are some of the key molecules.
Now, Doctor, the unknown unknowns, the mysteries that we do not yet know about that this telescope, as with previous instruments have done, will reveal even more mysteries. So how does one look for a mystery that you don't yet know exists?
That's a great question. I think what you're getting at is how do we position ourselves to be able to answer questions that we don't yet know we'll have? And that really boils down to the history of ground-based astronomy for 400 years. And that what every generation of telescopes seeks to do is jumping a leap in sensitivity and resolution that will allow us to see things we haven't seen before. And every generation of telescopes answers questions and shows us things that we weren't even able to conceptualize. Questions we weren't even able to conceptualize in the last generation. So with this telescope, we will reach a whole other level, make a next leap in sensitivity and resolution, and having the instrumentation to exploit that sensitivity and that resolution is what will allow us to address new questions we haven't thought of yet.
Now, in regards to exoplanet atmospheres, we have a set of planets in the solar system, some of them with atmospheres, or substantial atmospheres anyway. But do you expect to find atmospheric makeups on exoplanets that no one expected? Just really strange stuff. Do you think that's on the table, or do you think the universe is going to be more or less the same as the solar system as far as variation in atmospheres?
I think that we have found planets that generally fall into categories that were beyond what we would initially have expected from our own solar system and from our own theories, but they do fall into categories that are not so far beyond what we have imagined. So water worlds, gas giants, rocky planets, and the atmospheres of those are generally dictated by the chemistry and physics that we understand. So I'm sure that we will find surprises, but I think that they will fall into understandable ranges.
So you might find odd levels of something, some noble gas or something, but nothing that's going to scream, we don't understand that planet. It's going to be more like, we know what's going on there. But that's interesting. Now, Jim, I wanted to ask you were involved with a bunch of space telescopes, including fixing Hubble's vision back when that launched. What was that like? I mean, solving a problem of that magnitude, of fixing something that was defective in space.
Working to fix on Hubble was a very interesting experience. Of course, when we launched the telescope, we expected that everything would work according to plan. And it came as quite a surprise that there was a problem focusing the telescope. NASA had planned a backup camera for the telescope, which had been 60% complete. It was basically a clone of the original camera science instrument. And when the problem with the telescope was discovered, everyone scrambled to figure out, what could we do to fix the problem? It's not practical, for example, to carry another primary mirror up to the telescope and for astronauts to put that in. So the question was, can we figure out what went wrong that was causing the problem? Could we figure out a way in the backup camera that we could correct the problem? And could it be engineered in the amount of time that we had? NASA had scheduled a servicing mission for 3 years after the launch of Hubble. You have to remember the Hubble was envisioned to be visited by astronauts on a regular basis so that the science instruments could be replaced and upgraded and repairs made to the telescope systems. And the servicing mission, as they call them, was scheduled for 1993. And NASA was determined that they were going to go back up to the telescope in 3 years. And so the question was, could we figure out how to engineer a way to correct the problem? And so it was really a crash program. It's one of the fastest things I've ever been involved in. And because it was such a hugely visible program, Hubble was anticipated for many years before it was launched as a transformative, we talked about it being as big a step forward, as big an advancement beyond the best telescopes on the ground since Galileo first turned his telescope to the heavens. So the repair was something that was scrutinized by Congress and by the public. There were blue ribbon panels of Nobel Prize winners that were reviewing what we were doing. I won't say they were looking over our shoulder, but it was like working in a fishbowl. There was so much visibility and scrutiny on what we were doing. And we had very little time compared to what you would normally do to figure out how to redesign or rebuild this backup camera. So I had a role in one part of the system, building some active mirrors that we could control from the ground to make sure that the correction, the optical correction in the instrument would exactly cancel the error in the Hubble telescope itself. It's like subtracting two large numbers and trying to get zero. If any of those numbers is not exactly the same as the other, you won't get zero. You could get a big error still. And so we were very conscious of the fact that if we didn't get the corrective optics properly aligned with the telescope optics, that we could actually make the problem worse. So it was, I remember sleeping on a cot in my office many nights, having a great deal of anxiety about whether things would break on the vibration table as we were testing them. I remember being at the launch of the space shuttle and feeling the ground shake under my feet, and the clothes I was wearing vibrating just from the power of the rocket, being 3 miles away from the launch pad, and thinking there's no way anything is going to survive that kind of an environment, that kind of vibration. But when it all worked out, it was tremendously gratifying, and it was kind of like floating on air for a while when we saw the sharp images come back.
And sharp images they were. Hubble did more for popularizing science with the amazing imagery that it returned than a few other things. Now, Dr. Bernstein, with this telescope, 10 times Hubble, can we expect that again? Can we expect absolutely amazing photography?
Yeah, absolutely. I think we'll find that this is an eye-opening in the same way that Hubble was.
Now, Jim, you also, as I recall, worked with Kepler, which found an unbelievable thousands of exoplanets. Will these exoplanets that Kepler found be targets, or some of them anyway, or closer ones, be targets for the GMT?
I would say probably not. The average target star for the Kepler mission is about 1,000 parsecs distant. You have to remember that at the time we were building Kepler, we really had no idea how many or what type of planets form in what kind of orbits around various types of stars in the galaxy. So Kepler was a survey mission designed to answer that question. So it stared at one part of the galaxy, continuously measuring light from about 250,000 stars, waiting for planets to pass in front of the disk of those stars, and we would measure the dip in the light curve. So, what we now know based on the Kepler mission is that roughly half of stars like our sun will have a planet about the size of the Earth orbiting in the habitable zone. And so, that means we now know how deep we have to look into space to find the nearest exoplanets. And it's really the nearest exoplanets that telescopes like GMT are going to follow up on, give us the ability to measure the light from the planet itself as opposed to the star that it's orbiting. Proximity helps a lot, not being too far away for that. So Kepler was, really eye-opening in terms of understanding what exists out in the galaxy. And now the focus with missions like TESS that NASA has launched is looking for the nearby exoplanets, and the big ground-based telescopes are the ones that are going to really be able to do the follow-up and explore what the atmospheres of those planets look like.
What's next for GMT? Where is the timeline at right now as far as construction and building the mirrors? Where is it at now, and what's next?
Well, let me give you some updates on various parts of the project. So at the site in Chile, we have leveled the mountain. That was done a number of years ago. We actually leveled an area that's big enough for 2 GMT-sized telescopes. And we have excavated the foundation for the enclosure and the telescope pier. We've built the residence buildings to house the construction crew. We have a dining facility, a recreation facility. We're too far from any population centers for people to commute back and forth to the construction site. So we house the crew on site. That's all completed. The construction power infrastructure is completed. We're finishing now the water infrastructure. So basically, everything is set for the major construction to follow, and that will progress over a period of years. In terms of the optics, we have completed the first 2 of these giant primary mirror segments. Each of these segments is 8.4 meters in diameter. They are themselves, each of them, the largest mirrors that have ever been made in the world. 2 of them have been finished. 3 more of them are in various stages of grinding and polishing in the mirror lab in Arizona. So that makes 5 out of the 7. The 6th mirror is going to be cast early next year, and that'll be followed by casting the 7th mirror. So the optics are well along. We know how to manufacture them. We've proved that we can do that. In terms of these magical adaptive secondary mirrors that Rebecca was describing, these are the mirrors that have like 600 and some actuators in back of each one of them, and there are 7 of those up at the secondary. We have, I'd say we're about halfway through building a prototype of those mirrors, and we're going to now very soon start the long lead procurement and fabrication for the first production mirror. And those, by the way, are technology developed by a consortium in northern Italy. Our first light science instrument, which is called an Echelle spectrograph, and which will have a role in exoplanet detection and characterization through the precision radial velocity method, looking at the Doppler shift of the reflex motion, if you will, of stars that planets are orbiting. That instrument has completed its final design and is in the early stages of long lead procurement and fabrication. And then the telescope structure, this large, what we call the mount, which positions and controls the optics and the instruments, is under contract with a team of companies that are finishing their design, and then they will proceed into the fabrication of the mount. So there are various pieces of the telescope that are well along. There are other pieces that are still in design. And so we're progressing in parallel in various parts of the world, in Europe, in Australia, in Chile, in the United States. And if I had to give you a percentage, I'd say we're maybe 30% finished with the work that needs to be done.
My last question is for Dr. Bernstein. Once the telescope is finished, up and running, what's it going to be like for astronomers doing research with the telescope? Will they even need to go to Chile, or will the telescope remotely collect data and just send it to them? How will that work?
Well, like most ground-based telescopes, we'll have a proposal process, and there will probably be a fair amount of time on the telescope that goes to individual small projects, individual principal investigators, and small projects that can be executed in somewhere between a night and a few nights. And then there will be larger projects that involve large consortia of scientists across the partnership and between individual scientists across the partnership. But after they apply for time and get granted time, they will have a choice to go to the telescope and participate in observations, and to have the observations conducted remotely. And that is similar actually to the way it's largely done on telescopes today. Some observations are not that unusual or fairly routine, and the way that you collect the data is fairly predictable. Even if the science is very original, the kind of data that you need to get or the way you collect the data is fairly traditional, and it doesn't require a lot of unusual steps. And so in those cases, you can have either do the observations remotely or have the observations executed by experts at the telescope with, the scientist just sort of eavesdropping on the process. And I think that it will be largely the same as we use GMT. For some of the observations, they're more exploratory, or you need to make last minute decisions as the data is being collected. And for those, you may decide it's really worth going to the telescope, and you may decide that you can do even that in an eavesdropping mode with experts at the observatory. So I think all different strategies will be incorporated in the use of the telescope.
All right. I thank you both for joining us today, and I wish you great luck with the GMT.
Thank you very much.
Thank you.
Thanks for listening. I am futurist and science fiction
John.
author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Gautier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing, and be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?